Alright, so we're gonna learn more about set theory. Let's start. I wanna draw this and this guy right here. And you're all familiar with this already. This means for all x values, it satisfies p of x, and at least one value of x satisfies p of x. Now what I want to talk about is the idea of a restriction. So what do I mean by that? Well, X stands for any mathematical object, but sometimes we want to be dealing with a specific set of mathematical objects, such as numbers, or maybe you even want to study even numbers only, or maybe odd numbers only, or positive numbers only, or maybe you want to study vectors only. Then you'll be dealing with a specific set. All x values which are inside a particular set should satisfy p of x. So now what are you communicating? You're communicating that, hey, all of these mathematical objects which form a group right over here, like the group of numbers or the group of vectors, this group of mathematical objects satisfy p of x. And when you're saying that, you're saying the entire group basically, because it's all values of x. While over here, if you do a similar thing, then what is the idea that you're communicating? Well, you're saying that, hey, I have a group of mathematical objects right here, and I can tell you that there exists one element from that group which satisfies p of x. So these are the two ideas that you're communicating. And in both examples that I said, you are restricting your attention to only a specific set of mathematical objects. And of course, that depends on the context or the type of question that you're dealing with. So now I want to show that these are equivalent to another statement. So what is this statement? Well, basically we can just say that if x is an element of A, then p of x is satisfied. So now why are they equal to one another? Well, just think about it. What does this statement say? All mathematical objects, if they're inside of A, that means that p of x is satisfied. And what does this statement say? All objects inside of A satisfy p of x. That's just a different rephrasing, okay? Alright, so we can do a similar thing to this guy as well. And it's almost similar, okay? We can represent this as something like that. So the reason between the differences over here and over here, that's because over here we have that there exists at least one value which satisfies this condition, while at the top you have that all values or all mathematical objects x must satisfy this condition here as well. And like these things are necessary to place, because if you change this guy, for example, to an AND statement, then you're saying that all mathematical objects satisfy being a part of the set A. But that's just wrong, because the purpose of the set A is for you to restrict your attention towards a particular set of mathematical objects. Whereas if you change this to an AND statement, then this necessitates that all mathematical objects X should satisfy being a part of XA. So then it's no longer becoming a restriction anymore, because all mathematical objects satisfy being a part of A. So it just doesn't make sense. That's why you should say that if it is a part of A, then it is also a part of Px. So now you're not necessitating that all of X should be a part of A. You're saying if it is a part of A, then it should also be a part of Px. And at the bottom over here, well, you're not doing anything wrong, because you're saying that there exists one mathematical object which satisfies this condition over here, which, I mean, there's nothing wrong about that, because if you pick any mathematical object, well, certainly that's a part of some set that you're dealing with. If you happen to pick a vector, then it should be a part of a set of vectors, and it should satisfy some property, whatever it is. So like this at the bottom over here is true. So there exists a mathematical object x, which is inside of a set, and which satisfies a property. Alright, so let's dive into more set theory. So remember we introduced three set operations, the union, the intersection, and the takeaway operation. So these three, you take two sets and you're able to create a new set by using these three set operations. Now I want to introduce a new symbol, but the thing is, this new symbol is not a set operation. In other words, it's not used in order to create a new set. Rather, it is used to communicate a piece of information. So this new symbol has a shape like this, and you put one set on one side and another set on the other side. And you read this like A is a subset of B. So what sort of information does that communicate? What does it mean to be a subset? Well, if A is a subset of B, basically that means that A is inside of B. And I can illustrate that with an example. So if A is the set of the number 1s and 2, and B is the set of the number 1, 2, and 3, then A is a subset of B because the elements or the objects inside of A are also inside of B at the same time. Now, this also has a visual representation in terms of a Venn diagram. So if I were to draw a Venn diagram, and if I have B over here, then A would always be inside of B. So A has the numbers 1 and 2, and 3 is outside. So B contains 1, 2, and 3, while A contains 1 and 2. And it's easy to see that A is a subset based on this diagram. Alright, so now comes the question. How do we communicate that A is a subset of B in terms of logic? We have done so for the union, the intersection, and the takeaway operation. We know how to translate that in terms of logic, so let's try to do that for this scenario as well. Remember what we did last time in order to translate the set operations into logical statements. We said that if y is an element of a set A, then this was equivalent to y satisfying a certain set of conditions that we will call Py. While if y is part of an element of B, then it is equivalent to satisfying a different set of conditions which we will label as Q. So this is something similar that we did a couple of videos ago, and we're just going to skim through the details this time. So what does it mean for A to be a subset of B? Well, let's draw the Venn diagram again just to visualize things better. Are you going to agree with me when I say that if y is in A, then y should also be in B? Do you agree to that statement? Well, let's try to figure that out. So if y is in A, so y is somewhere over here, or it could be over here, or it could be over here. So these are the possible y values. Then are they also in B as well? Well, yeah, definitely, because you can quite easily see that based on the Venn diagram. So if this is correct, then this is also correct. But since this guy on the left is equivalent to this guy on the right, and similar to this guy as well, won't it be equivalent to saying that if P of y is true, then Q of y is true as well? And now that would be justified because these are equivalences, which means if I say if y is in A, then y is in B, that would be equivalent to saying if P of y, then Q of y. So, alright, what do we do next? Well, it's obvious. We already know how to express the if-then statement in terms of logic. We even have a symbol for it. There we go. So yeah, that's how we communicate this piece of information in terms of logical statements. Now it turns out we can be even more specific. So we can say if P of x, then Q of x. We used y as a variable before, but there's no reason that we could just use x instead, because you're more familiar with this sort of notation. Well, Actually, we can be even more specific than just stating it like this. We can say that for all values of x, this condition is satisfied. And now just think about it. If we go through all mathematical objects x, then we will find that this object satisfies it if it's inside of A. This object also satisfies that condition, so does this object, so does this object, so does this object. They all satisfy this condition over here. So then it's okay if we slap on this quantifier in front of this statement over here. And maybe it's much more clear if we replace these symbols with this instead. Because remember, because they're equivalent, we can just replace the symbols with this statement. So maybe this will be more clear to you. So for all values of x, if they're inside of A, then they're also inside of B, which is demonstrated by this diagram over here. Alright, let's try something else. Let's try to communicate the idea of two sets being equivalent to one another. So what does that look like? Well, let's show you an example. Okay, so this is an example of two sets which are equal, and it's obvious that they're equal. The question is, how do we communicate that in terms of logic? Well, here's an idea. What if we have, for all values of x, if x is in A, then x is in B, but it should also go the other way around. Alright, so does this condition satisfy whatever's at the top over here? So let's see if these two things are equivalent to one another. In other words, if this guy is true, then this guy should also be true. So we know that this is true already, because obviously these sets are equal. Let's see if it's true for the bottom case as well. For all values of x, if x is in A, then x is also in B. So let's pick a value of x. Let's pick the number 1. So if 1 is in A, then 1 should also be in B. So we can give a check mark there. But we should also go the other way around. If x is in B, then x should also be in A, which certainly is true as well. Because if the number 1 is in B, then the number 1 is also in A. So that checks out. But this should work for all values of x. So we can pick the number 2 as well. So the number 2, well, let's see. The number 2 is in A, so it should also be in B. That's check. And the number 2 is in B, so it should also be in A. So that's a check mark there as well. So both directions are satisfied. So that works as well. And it's obvious that it also works for the number 3. But what if we put the number 4 instead, or 5, or 6, since it should be satisfied for all values? How do we figure out if that condition is satisfied or not? Well, let's build a truth table, shall we? Alright, so this is the truth table over here. This is how it's supposed to look like. No problems there. So let's pick a value of 4. So x is equal to 4. So is 4 in A? Well, no, it's not. So that's false. Is the number 4 inside of B? Well, no, it's false as well. So we know that we're working at the 4th universe here. We're inside the 4th universe right now. So what does that mean? We're in the 4th universe. So inside the 4th universe, if A then B is true, if B then A is also true, so this statement is true as well. Which means that, well, it does satisfy the conditions for all x, because we check the numbers 1, 2, and 3, and we also check the numbers 4, and it's easy to see that 5, 6, 7, and -1, -2, and 0, and all those other numbers, they are part of the 4th universe right here, because all of these numbers, they're not a part of A, and they're also not a part of B. So we can safely say that they're part of the 4th universe, which means that these conditions are true, which means that this is true for all values of x, because we checked every single possible mathematical object already. So this is true, which means that this is true over here as well. Now, if you're not convinced, let's try this again, except let's make the top statement false. And how are we going to do that? Well, let's add a 4 over here. So now this is an incorrect statement, because these two sets are obviously not equal with each other. This means that if we were to work this problem out, we would get an answer that is false. So let's figure this out. Okay, let's pick the number 4, shall we? Because that seems like a smart example to use. So if x is in A, then x is also in B. Alright, which universe are we dealing with? Well, is the number 4 inside of A? Well, no, it's false. Okay, is the number 4 inside of B? Well, that's true. So we're in the second universe. But if we're inside the second universe, this means that the forward direction is true, but the backward direction is false. So this does not work for all values of x because the number 4 breaks this condition because it's false for the backward statement or the backward condition, meaning that the entirety of this statement is false itself because it claims that all values of x should satisfy whatever this condition is, and clearly the number 4 doesn't satisfy that condition, so we can safely say that this is false. So yeah, this is how we translate or communicate the idea of two sets being equivalent to one another in terms of logic. Alright, so we'll stop after we discuss one more point. And this one, well, let's consider this statement over here, but with a restriction. Okay, so we know what this stands for, we know how to interpret this, but let's consider if A is the empty set. Well then, what does this communicate? Well, this communicates that there exists a mathematical object x, which is a part of the empty set that satisfies the condition p of x. And there's something wrong with that statement, because it says that there exists a mathematical object within the empty set. Now, you know, the empty set is, well, it's nothing. It contains nothing inside of it. So you can't say that there exists a mathematical object inside of it. So automatically, we can just immediately say that this is false. And this is false for all possible cases. So this So in other words, this is a contradiction, which we have learned before in previous videos. Now, another thing to note is that it doesn't matter what p of x is. The condition here does not matter. So this could be, say, p of x and q of x or something like that. And like whatever condition this is, it's still false because the problem with this statement is not with the condition here itself, but with this portion right here, the existence of an object which is inside the empty set. Now that's just false, no matter what statement you're talking about or what statement you're dealing with. Anyway, let's consider the different quantifier, the A quantifier. Now what about this? What do you guys think? Do you guys think that this is also false? Well, I think that's the consensus here, but it turns out counterintuitively that this is always true. This is a tautology. Now there's really two different ways to explain this, and I think I will explain it in both ways just to convince you guys even further. Now, for the first explanation, we can represent this statement as, if you guys remember from the very start of the video, this is equivalent to this guy right here. And to show that this is a tautology, let's draw a truth table. So this is the truth table for an if-then statement. So if you prefer symbols instead of like math and set theory, you can just create a symbol q of x and give it the same meaning as this guy. If you're more keen to doing that, well, let's consider the first statement. X is an element of A. Well, this is going to be false no matter what, because A is the empty set. So we can't be at the first universe, nor can we be at the third universe. So this guarantees that we're at the second universe or the fourth universe. But notice, let's just cross the first and the third row out, because we are not in one of those universes. Alright, so notice the truth table for the third column. Well, the third column it's all true. There are no false instances. And look, we're either at universe number 2 or universe number 4. It doesn't matter which we are at. This will always be true no matter which universe we are in. So that's it. This is always true. So yeah, that's one way to explain why this is always true. So if you're not convinced yet, there's a second explanation. So this thing is equivalent to this guy, right? And you all agree to that because the two not signs, they cancel each other out. The thing is, we can bring one of the not signs inside, and when we do that, we just have to change the quantifier from an A to an E, and the not sign goes back, and we have this statement over here. Now let's put brackets here just so that it's easier for me to explain. And now just see, this statement over here, it's pretty similar to what we have at the top. The only difference is with the proposition. But remember what we said earlier, whatever the proposition is, it doesn't matter, because the mistake here is we're claiming that there exists an object inside of the set A, which is the empty set, and that can't possibly happen. So no matter what the proposition is, whatever's inside is always going to be false. And since we reverse that, it's always going to be true because of the not sign over here. And that's just another explanation of why this is always true. Now before we leave off, I think let's do one example just to consolidate this piece of knowledge. So what did we say earlier? This guy over here is always true. No matter what p of x is, it's always true. So let's assign a meaning to p of x. So let p of x be equal to x being an element of b. So now this is a statement. This says that x should be an element of b. That's the condition that needs to be satisfied. So remember, we can write this like this guy over here. And since p of x is just x being an element of b, so we can say that for all x values, if x is in A, then x is also in B. Now this is exactly the definition of a subset, and this means that A is a subset of B. And turns out this is always true. So since A is the empty set, we can say that the empty set is always a subset of B. Now we didn't specify what the set B is, but we can assign any meaning to the set B. We can say that it's the set of numbers or the set of shapes or the set of whatever, and this will always be true because this does not depend on this proposition. And the intuition behind this is rather simple. So let's say if you have the set like 1 and 2 as A and B as 1, 2, and 3, then will you agree that if A and B are subsets, then B union A is always the same as B? Well, this is true because there are no new elements from A. So if you take the union between B and A, you won't get anything new because A is just simply a subset of B. It doesn't have any new elements inside of it. Well, clearly, B union the empty set is still the same as B. So therefore, the empty set must be a subset of B because it satisfies this condition. So by that argument, the empty set is a subset of B, and by this argument as well, the empty set is also a subset of B. So there are many different ways where we can explain this, and I hope that through these many different explanations that helps you practice your way of thinking in terms of logic and all that other stuff.